Today we're going to talk about random variables. Let's see. So what's a random variable? A random variable, you have a sample space. Imagine we have a probability here, and a random variable is a function mapping points of the sample space into real numbers. So this straight line here is the set of real numbers. Each little omega, each element of my sample space is going to be mapped into some point of the real line. Okay? So you could think, for instance, if omega is the population of the world, right? You pick some random person in the world and we measure, say, how high the person is. Okay, so that would be an example of one random variable. Another example would be pick a person and measure the weight of the person, for instance, okay, or the blood pressure. Whatever is the characteristic you want to analyze statistically, it could be a random variable. So you could define a random variable as any function mapping points of your sample space to real numbers, okay? All right, so this, and you usually denote a random variable by a capital letter, like capital X or capital Y or capital Z, okay? It's usual to use uppercase letters, okay, for random variables. So here I have in black this function, capital X, mapping points of my sample space to the real numbers. Then I have this function little g mapping real numbers into real numbers, okay? So I have a random variable from my sample space to real numbers. Then I have a function taking real numbers into real numbers. And then I look to the composition, y equals g of f. I apply first x, and then whatever I get, I apply the function g to this point. And I get to g of x of omega. Okay, I start with omega, I apply x, I am at x of omega, I apply g, I end up with g of x of omega. G evaluated at x of omega, the composite function. Okay, and then we can think about this process, to this two-step process, as another random variable, because in the end we are mapping points of my sample space like little omega points of the real line into a real number. So this is a real number. Okay, so we think about this composition as the capital Y equals the, first you apply omega x and then you apply g. So this is another random variable. Okay, so you can build random variables from other random variables by applying function. For instance, I can pick up some person in the world, measure how high the person is, and then add 7 for no good reason, whatever, okay? And then I find the height plus 7. Or I can square, or I can apply any mathematical function g to this. A little technical note, usually this function here has to be measurable, but we are not talking about sigma algebras, and so forget about that. Let's make it really simple for us. A random variable is going to be any function mapping points of my sample space into real numbers. Okay, so it's a function mapping points of my sample space omega to real numbers, and this y here is also going to be another random variable mapping points from the sample space to real numbers this way. First you apply g, then you apply some function g. Well, I'm sorry, first you apply x and then you apply this g function to apply this random variable y. Now, let's look at an example here. What do I mean by this square brackets x is smaller or equal than x0? So first, by x0, think of x0 as any real number, okay? Pick any. Let x0 be any real number, and we can look at this. This is going to be an event. This is going to be a subset of my sample space. It's made of all elements of my sample space such that when you apply the random variable x to this omega, you find a real number smaller or equal to this x0. Okay? So this is short notation for this. Another way to do that is the inverse image of that set here. All the omegas that when you apply x, they are going to end up in this interval. They are going to be from minus infinity to x0, including the x0 potentially. Okay, so quick example to see if you are understanding. Tell me, what do I write here in the middle? So if I have this event and this is another event, these are all the states that when you apply the random variable, I get 7 or less. This is short for all the states, for all the little omegas, such that when I apply the random variable x, I get to 8 or less. So what should I do? Are they set equal? One is a subset of the other. What happens? Okay, so if when I apply the random variable, I get from 7 or below 7, I surely am in a point where I'm from 8 to below. Okay? So if I'm in this set, then I am in this set here. So this is a subset of that. Okay? Potentially a proper subset could be the same if the random variable has no point that maps between 7 and 8. Sometimes, writing this notation, you have to be very careful solving problems. Let me give another example. X squared smaller or equal to 4. So x squared is an example of x, and then apply a function. In this case, squaring means this function g takes a number and squares it. Okay? So this is the same as this, right? I just subtract 4 from both sides, also I don't change the inequality. And then I construct here the parabola, x squared minus 4 as a function of x, intercepts the x-axis at 2 and negative 2. It's easy, right? We know that x squared minus 4 is x plus 2, x minus 2, and if this is 0, if and only if this number is 0 or this number is 0, if this number is 0, we are at minus 2, x plus 2 is 0, means x is minus 2, and if this is true, x minus 2 is 0, then x equals 2. So are the points that the parabola intercepts the x-axis. So instead of writing this, we might write that, so we have an explicit x here. So that trick helps in problems a lot. You should be aware that you might have to do some algebraic manipulation in solving problems. Okay? Let's see another example. So let's say my random variable is the outcome of an honest die. Dice, you play and you get the result 1, 2, 3, 4, 5, 6, and it's honest, meaning it's the equal chances of any outcome. So let's let the pk be the probability that the outcome of my die is exactly k. K could be any number from 1 to 6, integer number, right, from 1 to 6. And what is the value of the pk? Well, I know the sum of all possible outcomes has to be 1, right? These are disjoint outcomes, right? I can write my sample space as 1 union 2 union union 6. So the probability of having anything is 1. This is the probability of the entire sample space. And this is the sum of the probability of 1 plus the probability of 2 plus the probability of 3, etc., up to the probability of 6. And I know that the dice is honest, so meaning that all probabilities of each side is the same. So I have a system with 6 equations and 6 variables, It's a linear system, easy to solve. There's a unique solution. The solution is each pk is 1 over 6. Okay, the probability of having 3 is 1 over 6. The probability of having 5 is 1 over 6. The probability of having 1 is 1 over 6. For all k, the probability of having k as the outcome is 1 over 6. That's what we refer to as the uniform distribution in a finite set, where each point has exactly the same probability at any other point. Okay? So, quick problem here to finalize. What's the probability that we have an even outcome? When we throw honest dice, what's the probability of an even outcome? So even outcomes means the outcome is either 2, 4, or 6. That's the probability of 2 plus the probability of 4 plus the probability of 6. Each one of them is 1 over 6. So we have total 3 over 6 or 1/2, 0.5 as the probability. Okay? Now, let us see an important concept. When we have a random variable, we focus on the sets, on events of this format here. The random variable is smaller or equal than some number. Why? Because this is going to help us with the cumulative distribution function of a random variable. So if you have a random variable associated to this random variable, we have the CDF. CDF for cumulative distribution function, the initials of cumulative distribution functions. The CDF of the random variable, it's going to be exactly this. Capital F of this. So we usually use the capital F for CDF. We put the random variable here as an index and the argument of the function. And it's just a probability that our random variable is smaller or equal than the argument, x0 here. Okay, so this is the definition. This is one of the most important definitions. Please memorize that. This function here takes real numbers into real numbers, and it has some properties, some important properties. It's weakly increasing, okay, and we understood that the last time. If x0 goes up, this probability here will go up or stay the same. So that's what I mean by weakly increasing. Either when the argument here goes up, the function f of x0 either stays the same or it goes up. Okay? It's right continuous. The limit of this function when your argument goes to minus infinity, it's gonna be 0, and another property is that the limit of your cumulative distribution when the argument goes to infinity, it goes to 1. Okay? So this and this happens because it's a probability in the end of the day, right? So this has to be always, always, always in the interval from 0 to 1 because it is a probability. Okay? All right. Now with knowing these basic properties of the CDFs, of the cumulative distribution functions, let's look at the graph here and see what things that can happen. So one thing that can happen is like the green line, the function is going up, asymptotically goes to 0 at minus infinity, then when x increases it goes up, but it can jump. So there's a discontinuity here at this point. It's a jump discontinuity, okay? And asymptotically goes to 1. Or it could, for another random variable, it could have 0, 0, 0, 0 values up to some point and then goes up, and then after some point it equals to 1, okay? So let's work in detail our main example where you throw an honest die, right? The outcomes can be 1, 2, 3, 4, 5, 6. And I'm plotting the cumulative distribution function of this random variable, the outcome of an honest die. Okay? All right? So what's going to happen? What is the probability when you throw an honest die, your result it's smaller or equal to 0? It's 0, right? The smallest you can have is 1, so the chance that you are below 0 is 0. All the way up to 1 here, except when we reach 1, we jump, right? The probability of having an outcome smaller or equal than 0.999 is 0. And the probability of having an outcome smaller or equal to 1, well, 1 is smaller or equal to 1, so then you have probability 1 over 6. So at this point here, there's a jump in the probability on the CDF, and the CDF becomes equal to 1 over 6. Until we approach 2. What's the probability that when we throw honest die, the outcome is smaller or equal to 1.99? The only possible outcome smaller or equal to 1.99 is 1, so the probability is 1 over 6. Now, on the other hand, what's the probability when you throw an honest die, the outcome is smaller or equal to 2? It could be 1, it could be 2, so you have 2 chances in 6. So at this point here, the function jumps all the way to 2 over 6. From 1 over 6 to 2 over 6. Stays the same until it reaches 3. It jumps. Stays the same until 4. The probability then jumps up. Stays the same until 6. The probability jumps at 5. And then stays the same until it gets to 6. And then the probability becomes just 1, right? So for instance, if you are here, 5.5, what's the chance of you throw the random die and the outcome being smaller or equal than 5.5? Well, the outcomes that are good are 1, 2, 3, 4, 5, so you have 5 chances in 6 of your outcome being smaller or equal than 5.5, okay? And if you pick a number here bigger than 6 or equal to 6, what's the, say 7, what's the probability when you throw the honest die, you get a result smaller or equal to 7? 100%, you always do. You always get something smaller than 7. So the function becomes 1. So that function is not continuous, it is right continuous, because at any point when we approach 5 by the right-hand side, the function is continuous by the right-hand side, not when we approach from the left. The function has a jump up at 5, okay? So this is a function which is not continuous, but it is right continuous, okay? When x goes to infinity, the function is 1. When x goes to minus infinity, the function is 0, okay? And of course, the function is weakly increasing. When you move to the right, either the function stays the same or it moves up. So it is weakly increasing function, okay? Hope you enjoy. Bye-bye.